Pouring temperature. Pouring temperature refers to the temperature of the molten metal before it is poured into the mold. The pouring temperature has to be higher than the solidification temperature of the metal in order to allow the free flow of molten metal into all regions of the mold cavity well before solidification is completed. However, it must be noted that the temperature difference must not be too high as heat from the mold cavity has to be quickly removed in order to speed up the solidification process. The difference between the solidification temperature and the pouring temperature of the metal is designated by the term superheat, which is the most important parameter to be considered in melting and pouring operations. For example, aluminum alloy has melting temperature of 660 degrees Celsius with its corresponding pouring temperature range between 700 degrees Celsius to 750 degrees Celsius. For better end results, it is desired to pour the metal at the lowest possible pouring temperature. The pouring temperature is estimated by taking into consideration the various factors like melting and freezing temperature of metal, heat loss due to the transfer of metal through ladles and mold, the shrinkage behavior of the pouring metal, and thinnest sections of cast part. In order to protect the molten metal from losing its heat, it is always covered by exothermic compounds, which are mixtures of metal oxides and aluminium. Stir casting. Foundry practice has led to various technological advances with respect to materials and processes from which metals can be effectively and economically cast. Stir casting is one of the advanced liquid cast metal technology in producing aluminum based metal matrix composites by employing stirring principle of liquid metal. The concept and benefits of stirring or agitation of molten metal goes back to the foundry age where stirring of liquid metal was accomplished by lance gas injection into the liquid metal. Stirring action within the molten metal helps in easy mixing and melting of alloys as well as homogenizing of temperature throughout the furnace. Although successful to a quite extent, the process suffered from limited effectiveness as well as increased dross formation. However, the concept gave way to new technologies, and today, advanced subsurface steering technologies like pneumatic jet steering, electromagnetic approaches, and rotary devices have been employed for steering purpose. Operation. The schematic representation of stir casting process is illustrated in its simplest form. The arrangement consists of a furnace inside which a graphite or cast iron crucible surrounded by a coil of copper wire is placed. The crucible holds the charge of metal to be melted. A powerful alternating current flows through the coil of the wire, creating a rapidly reversing magnetic field that penetrates the metal. The magnetic field induces eddy current and circular electric currents inside the metal by electromagnetic induction, thereby producing stirring action within the molten metal. Meanwhile, the reinforcements or alloying elements are added to the molten metal and then stirred continuously by means of a stirrer for a short duration to create a vortex that the then forces the slightly lighter particles into the melt. The molten metal is then transferred into a preheated ladle and then and oxygen inert gas like argon gas is used. Meanwhile, the reinforcements or alloying elements are added to the molten metal and then stirred continuously by means of a stirrer for a short duration to create a vortex that forces the slightly lighter particles into the melt. The molten metal is then transferred into a preheated ladle and then poured into the mold of the desired shape. Since aluminium reacts rapidly with the surrounding oxygen, an inert gas like argon gas is used as the carrier gas to assist injection of the alloying elements, reinforcements, and pouring metal in a clean form. Note, an interesting development in stir casting is a two-step mixing process. In this process, the aluminum matrix material is heated to above its liquid temperature so that the metal is totally melted. The melt is then cooled down to a temperature between the liquids on solidus points and kept in a semi-solid state. At this stage, the preheated reinforcement or alloying particles are added and mixed. The slurry is again heated to a fully liquid state and mixed thoroughly. This two-step mixing process has been used in the fabrication of aluminium. Advantages of stir casting: stirring action within the molten metal helps in easy mixing and melting of alloys as well as homogenizing of temperature throughout the furnace leading to sound castings. Stirring action helps in removal of hydrogen gas, eliminates porosity, better dimensional control and tolerances in casting, clean and sound castings can be obtained. Disadvantages: equipment is costlier, excessive stirring can increase gas pickup, furnace lining wear, and oxidation of alloys. Stirring speed and time has to be monitored appropriately as it has a direct influence on the hardness of the cast metal. Monitoring an inert gas atmosphere is an additional requirement.